This implementation probably feels fairly natural to someone from, say, a C or Java background. But if we measure the execution time of this code for a large input, we say we see that this operation is very slow, perhaps surprisingly so. We'll benchmark this with IPython time it magic, which has been discussed earlier. Okay, so now back to the codes. Big, let's go array equals to nb dot random dot rand int the bracket 1 to 100 size equals to 1, that's 1 million. Time it, compute reciprocals, big array. Now give some time. Okay, so it takes several seconds to compute these million operations and to store the result. When even cell phones have processing speeds measured in gigaflops, that is billions of numerical operations per second. Here we got the result 3.61 seconds plus minus 664.6 meter per second per loop, which is mean plus minus standard deviation of 7 runs in one loop each. Okay, so this seems almost absurdly slow in the gigaflops of the mobile phone speeds. It turns out that the bottleneck here is not the operations themselves, but the type checking and function dispatches that CPython must do at each cycle of the loop. Each time the reciprocal is computed, Python first examines the object's type and does a dynamic lookup of the correct function to use for that type. If you were working in compiled code instead, this type specification would be known before the code executes and the result could be computed more efficiently. Okay, now let's introduce ufuncs. Introducing ufunctions, known as ufuncs. So for many types of operations, Numpy provides a convenient interface into just this kind of statically typed compiled routine. This is known as vectorized operation. You can accomplish this by simply performing an operation on the array, which will then be applied to each element. This vectorized approach is designed to push the loop into the compiled layer that underlies NumPy, leading to much faster execution. Okay, so now let's compare the results of the two codes. Print okay, so compute reciprocals values, print 1.0 values. This gives the answer this one, as you can see here. So looking at the execution time for our big array, we see that it completes orders of magnitude faster than the Python loop. Now we will use the timeIt function. One point oh big array. Now it will take some time. So vectorized operations in NumPy are implemented via ufuncs. We got the answer 6.24 ms plus minus 61.6 I guess it's microsecond per loop, and it goes on. So vectorize, and we were discussing that vectorized operations in NumPy are implemented via ufuncs, whose main purpose is to quickly execute repeated operations on values in NumPy arrays. So ufuncs are extremely flexible. Before we saw an operation between a scalar and an array, but we can also operate between two arrays like this. Np dot arrange 5, np dot arrange 1 comma 6. So we got output this 0 to 0.5, then 0.66667, then 0.75, then 0.8. So, and ufunc operations are not limited to one-dimensional arrays. They can act on multi-dimensional arrays as well. X is equals to np dot arrange 9 dot reshape to use directs x gives the output this. So computations using vectorization through ufuncs are nearly always more efficient than their counterpart implemented through Python loops, especially as the arrays grow in size. Anytime you see such a loop in a Python script, you should consider whether it can be replaced with a vectorized expression.